Hello everybody and welcome back to another RevWise video. Today we have an IB Chemistry higher level specimen paper, specifically a paper 1B. So if you're looking for paper 1A, we did that in a previous video, so please refer back to that video if you want the solutions for it. That's the multiple choice paper, but now we have the paper 1B. So yeah, like the previous papers I've done, I'm just going to go into it completely blind and show you guys how to work through each of these questions. So let's get right into it. Okay, question 1. Hypochlorous acid is a sterilizing agent used in swimming pools and is produced when chlorine reacts with water. Deduce the oxidation states of chlorine in the reactants and products of this equation. Okay, so first we have the reactant, which is just simply Cl2, diatomic chlorine. So we should know that since it's just Cl2, oxidation state here is going to be 0. Interesting 0 I do there. And then we have HOCl, so let's calculate it here. So H will give us +1. O minus 2, and to balance it, we need a +1 for the chlorine. So chlorine is going to be +1 here. HCl, H is going to give us a +1, and Cl has to balance that +1, so it's going to be a -1. There we go. Explain why more chlorine reacts with water when NaOH is added. So let's look at the equation. So more chlorine is reacting with water, meaning the equilibrium is going to do this, is what it's saying. Why would that happen? Well, it would happen if we're losing our products. And if you see here, both our products are acid, and we're adding a base, which is NaOH, strong base. So what's actually happening is the NaOH is neutralizing these acids, which is causing the equilibrium to shift to the right to replace the lost acid. So how can we explain that? Well, we can just say that the equilibrium shifts right, or towards the product side, however you want to say it. And then this is because our products, or our HOCl plus HCl, are neutralized, or the H plus is being removed from it. Okay. Researchers studying the solubility of chlorine in pure water at different temperatures compiled the following data from different sources. So different temperature, okay, and then it's giving us these different sources and different solubilities, sure. Identify a problem when comparing the data from different sources. Let's have a look at our data. Yeah, so clear problem here. You can see these are all the same measure, solubility, but we can have grams per 100 centimeters cubed, centimeters cubed per 100 centimeters cubed, grams per 100, milligrams per 1,000. These are different units. Makes it confusing to compare, which is a simple problem. Different units. It's a 1 marker, right? Yeah. So, I mean, there's probably other things you can say. I'll try and find at least one other one. Yeah, so another issue here, you can see this is 6,300 milligrams, and then here we have 0.57, 177, different degrees of accuracy. They're not to the same significant figures, which is another issue. Okay, units of solubility are converted to moles per dm cubed. Complete the table by calculating the value for source E. Assume the density of chlorine is that at 30 degrees Celsius. Okay, and then it's asking for E, which is 30 degrees. Okay, so the way we do this is first we have to remember that 177 centimeters cubed equals to 0.177 dm cubed, right? And we have this. And how are we going to get a value for the mass from this? Well, we have the density, right? And remember, density equals mass over volume, meaning if we want the mass, we need dV equals M. So we have our V, which is the volume, and we're just going to times that by our density, which is 2.86 grams per dm cubed. And that's going to give us a value of 0.506 grams. And 0.506 grams, with that we can calculate our concentration. First, we need to get the moles, right? So to get the moles, we just divide it by our molar mass for chlorine, chlorine gas in this case, which is Cl2, so which is going to be 70.9, and yeah. And then we're going to convert this to a concentration, right? So converting to concentration, that would be the same as timesing it by 1 over the volume, which is 100 centimeters cubed, also known as 0.1 dm cubed. And that's the same as essentially if we just did this, which is 0.506, that times 0.1. Yeah. and that gives us an answer of 0.0714 moles PM cubed. Okay. Suggest an explanation for the effect of temperature on solubility. So what kind of effect do we have here? So we're increasing temperature and it looks like solubility is decreasing. So why could this happen? Well, the solubility is just determined by this dissolution reaction, right? So essentially this is our dissolution, right? Basically this is the solubility, this forward reaction. And when we're increasing temperature, it's telling us that our solubility is decreasing. So this could happen if this dissolution reaction is exothermic. So if it's exothermic, that means that at a higher temperature, the equilibrium is going to shift towards the reactant side. So when we increase our temperature, our equilibrium is going to shift towards this side to compensate for the higher temperature, right? So if this is exothermic, this means this is endothermic. And therefore, this reaction would be favored when we increase the temperature. So that's one good explanation to why the effect of temperature on solubility. So exothermic dissolution. I won't write too much because I explain it verbally, but yeah, essentially that's what we're talking about here. There's the dissolution reaction that's exothermic. Why chlorine is not often added to swimming pools directly. Oh, this is a pretty simple one. It just the fact that chlorine gas is toxic gas produced. Yeah, CO2 gas. Okay, HOCl ionizes to form hypochlorite ion, which is a less effective disinfectant than undissociated acid. Graph shows the concentrations of HOCl and OCl minus at different pH values. Okay, deduce the pH range where water is most effectively sterilized. Yeah, so as you see here, we basically want to have the highest concentration of HOCl, right? Because that's the concentration where it is most effectively sterilized. So let me just erase this. So we're looking for when HOCl is maximum, which is here. It starts dropping off around here. So basically, where is HOCl highest? Looks to be around here. So around here, we'll have the highest concentration of HOCl, meaning that and we know it's a more effective disinfectant than than this. So essentially, the range is going to be pH 0 to pH 6. Determined with reference to the graph in E, the pKa of HOCl. Okay. So essentially, the pKa is going to occur at a point. The pKa is going to equal to the pH when these two concentrations are going to be equal. We can see this is the point where they're equal, and this is the point where the pH is going to equal the pKa. So if we go here, we can see it's going to be 7.5. 7.5. It wants us to refer to the graph. I assume it just wants us to draw it on the graph, but if we want some other way of showing it, we can say Cl minus is equal to our HOCl. Yeah. And this is our pKa. Yeah, okay. Ammonia released from sweat and urine reacts with HOCl to form a range of compounds including and chloramines. Deduce a reaction for the formation of dichloramine NaCl2 from ammonia and HOCl. Okay, this isn't too bad. So we have ammonia and HOCl. So ammonia, we have NH3. That's going to be aqueous. And then we're going to add that to our HOCl, which is also going to be aqueous. Thank you. It's going to form, our NaCl2. And it is also going to form water, it seems like. Yeah, because we have this base and our acid. We're forming NaCl2 and water. This is not balanced, it seems. To balance it, it's not really a trick I can give you for just general balancing. You just need to figure out how to do it in whatever way suits you best. For me, I just try to think of it in my head. Looks like we can put a 2 here and a 2 here. 1, 2. Yeah, okay, looks about right. Oh, I didn't put our state symbols here. This would be aqueous, this would be liquid. Yeah. The graph shows the molar ratio of chloramines formed at different pH values at 25 degrees Celsius. Trichloramine and NCl3 causes pool water to smell bad. State 2 conditions needed to prevent the bad smell. Okay, so this is the one that causes pool water to smell bad. So just based on here, we're looking for places where we can prevent the bad smell. So where is the concentration lowest, right? So it looks like it's very low past pH 5. So this point onwards, it reaches basically a minimum. So one condition we can say is that we want a high pH, right? pH greater than 5.5, around that. Yeah, I wanted to say pH greater than 5 because it's not really clear at what point this is. But pH greater than 5, that will work, or keeping a high pH is one condition. What other condition could we have? Well, let's see. Yeah, so we know that these chloramines are formed from this previous reaction, right? Different chloramines are formed at different pH values. So a simple way we can prevent it is by just preventing the reactants from producing this chloramine. So any of these reactants, chlorine, Cl2, HOCl, NH3, I would just say, yeah, NH3, because it's like the main reactant which produces it. So low concentration of NH3. Yeah, because if we have a low NH3, we can produce this NCl3, which means there would be also a low concentration of NCl3, which means there would be no bad smell. So just two reasons why operating a swimming pool at a lower temperature is favorable for the environment. Why would this be favorable? Just off the top of my head, when they say environment, I would just think of lower energy consumption, because it takes energy to keep it at a higher temperature, right? If you're heating the pool. Okay, what other reason at a lower temperature? I think in this previous, yeah, it talked about how solubility of chlorine is decreasing at higher temperatures because the dissolution reaction is exothermic. So we can say that the solubility of chlorine is higher. And that's going to mean that we lose less chlorine, it's more efficient. Yeah, that's pretty 2 good marks. It's 2 marks, right? Yeah. Student investigates the effect of exposure to the air on the ascorbic acid concentration in specific orange juice. Equal volumes of orange juice are sealed into identical flasks and placed in a refrigerator for 2 weeks. The samples in the refrigerator are exposed to the air by removing the stopper for a number of hours in a day. Okay, 2 variables that are controlled. Okay, pretty simple. One variable, we can easily say that temperature looks like it's going to be controlled. They're all in the same environment. We're directly controlling that. And we're using orange juice, right? Yeah. So I guess type of orange juice. Source of orange juice, however you want to say it. Does it say if it's like freshly squeezed or if it's a bottle orange juice? It says, okay, it says a specific orange juice. So, yeah. Oh, yeah, you can also say initial volume, because it's telling us we're using identical flasks, so it means that the volume is going to be equivalent if we're doing it to the same point. What else can we say? Yeah, I think this is pretty good. Oh, surface area, same flask. Yeah, a lot of them apply the same flask, but these are 2 easy ones to get. So, okay, concentration of ascorbic acid is determined by titration with a standard iodine solution, sure. Every few days, 10 cm cubed of orange juice is removed from the sample, diluted to 100 cm cubed, then titrated. Suggest why the juice is diluted before titration. Why would it be diluted before titration? Well, dilution is essentially here. It's giving us a larger volume of the juice. So when we have this larger volume, it gives us more room to work with. We can perform multiple repeats. So it allows us to conduct multiple titrations. Just off the top of my head, usually when we dilute something is because if we add indicator to this and it's too concentrated, it's hard to reach an endpoint that's determinable by like the human eye. So essentially, if it was too concentrated and we added a bit of our indicator, it would just instantly change color, which would make the endpoint quite hard to determine. So yeah, by diluting it, we have an endpoint that's easier to see. Identify a possible systematic error with this method regarding the sample that is exposed for 0 hours. So we have this sample that is exposed to 0 hours. Systematic error. Interesting. So what could it be? Okay, I see it. So this sample is meant to be 0 hours, meaning it's not exposed to the air at all. But in order to conduct our titration, in order to actually withdraw the sample and actually investigate it, we have to unstopper the flask, right? So it's going to give it some exposure. So some air exposure is to retrieve samples. Yeah, pretty good question. Okay, suggest how an additional flask could be set up to verify whether the systematic error in II has occurred. Okay, so we're looking for a way to retrieve. Looking at a way to verify that this air exposure hasn't impacted it. So well, how could we do it? How could we retrieve the sample without... Okay, so they're using a stopper here. So there are stoppers that have a hole in them, allowing us to insert a syringe, and then we can essentially not open the flask, put a syringe inside, withdraw the sample, and do our experiment on that, which allows us to verify that hasn't occurred. So I would say use a syringe without removing the stopper. What other solutions could there be? Yeah, you could also just I guess, I mean, it's quite simple, but if you just have another sample that you only titrate once after 2 weeks, it would have the same effect as verifying that the systematic error hasn't occurred. And yeah, those are two possibilities. Yeah. Okay, we have this data from a titration. Percentage uncertainty of the titer. Okay, so we have final burette reading of 16.1 plus 0.5, and we have initial of this and percentage uncertainty. Okay, so the combined uncertainty of both readings is going to be 0.1. Oh, that looks like 6. 0.1, and then essentially the actual volume of the titer is going to be the final minus initial, which is going to be 15 centimeters cubed, and this is 0.1 centimeters cubed. Okay, and percentage uncertainty, so we're just going to put our combined uncertainty over our measured, just that, and then percentage, so times 100 gives us 0.7 roughly. Okay, so following graph shows the student's results. Okay, calculate the average rate of decrease in the ascorbic acid concentration for the 24-hour sample of the 14 days, including units. So 24-hour sample is triangles over the period of 14 days, an average rate of decrease. Okay, so average rate would means we have to do just rise up run. So we have our initial, which is here, looks like it's gonna be 5.3, and what do we finish on? Looks to me around 1.1. Yeah, because I drew it at like the top edge of this triangle, right? So it's gonna be around 1.1. And units are times 10 to the minus 3, right? Yeah. So we have 5.3 times 10 to the minus 3 minus 1.1 times 10 to the minus 3. And then that's all over our time duration, which is 14 days. You can just leave it as days because that's going to be our final unit. And if we add that to our calculator, we get 3.0 times 10 to the minus 4, and including units. So our units are going to be, this is going to be rate of decrease. So this mole TM cubed, and this is going to also be per day, right? Because we did it based on days, so per day. Yeah, pretty simple. Yeah, let's move on. Students' hypothesis: a lower ascorbic acid concentration will be found in juice exposed to the air for longer due to oxidation of ascorbic acid by oxygen. Discuss whether or not the data supports the hypothesis. Okay, so we found juice exposed. So it looks like the juice exposed for 24 hours is looking like it's having a large decrease in ascorbic acid concentration, has the lowest, and it looks like it's proportional. So 8 hours has a lower, 2 hours has, 8 hours is higher, 2 hours higher than that, 1 hour higher, and then the highest is 0 hours. So what can we say? We can say that because they usually want something that's quite like critical in the way you answer this. So one part of it is that it supports it because basically longer exposure per day leads to reduced ascorbic acid concentration. But remember, the hypothesis is specifically due to oxidation of ascorbic acid by oxygen. So our point against is that there is, however, no direct evidence of oxidation of the ascorbic acid, right? So like we can see that it supports this first part, that it's a lower ascorbic acid concentration will be found in juice exposed to air for longer. But this oxidation part, we have no evidence. We just see the concentration, so we can't comment on that. We can just say that there is no evidence for the second part. State the implications of the results in the experiment for avoiding loss of vitamin C in the storage of orange juice. Pretty simple, I guess. Just don't store, you shouldn't store orange juice in unsealed container, or the converse. You should store orange juice in a sealed container. Just drink it quickly after you open it. Suggest an extension for the investigation that would generate further recommendations for the storage of orange juice. I guess this is actually quite vague, but there's loads of things you can say just off the top of my head. Temperature, yeah. Temperature. Of course, you would actually explain. So you could say like, oh, the effective temperature can be used to verify effect, importance of refrigeration of orange juice, right? Just something like that. Light intensity can be used to verify the effect of having your refrigerator light on, right? Something like that. So we're giving our variable here that we want to investigate, and then we also want to talk about why this is important to generate future recommendations. A student investigates the effect of pressure on the volume of carbon dioxide gas released from a carbonated drink poured into a flask. To alter the pressure on the carbonated drink, masses are placed on the top of the piston of the gas syringe. Okay, I understand. And the graph shows some of the data collected. Okay, determine by annotating the graph the initial release of CO2. So it looks like it wants to draw a tangent here for experiment 1 to get the initial rate. So let's just do that. So let's get our ruler, match it up to the initial, which is time equals 0. It's like around here. Oh, it needs to be a bit steeper. Sorry, this is a bit hard to function. Yeah, there we go. Let's draw our line. Okay, what does that give us? So 40 and whatever's here. 30, 35. 35. So, do we have a box here? No? I guess we just have to write it down. So this is 40, 35. So that's going to be 40 over 35, which is 1.14 and cm cubed per second. Okay, nice. Estimate the time at which the piston would begin to move if a 600 gram mass is used. 600 gram mass is used. So what is our current mass? Masses. Oh yeah, so this is 200, this is 400. Experiment 2 is 400, 200, 400. So if we increase it to 600, and it wants us to estimate what time the piston will begin to move. So this is our, so it's going from 0 to 10 to around 25. So I would say something around like 35 seconds, right? Because based on that, or we can say like 40 seconds based on the previous patterns. So just 2 reasons why the volume of CO2 collected in the gas syringe is smaller when more masses are placed on top of the piston. So when we're adding more gas, why volume collected is smaller? So if we adding more, okay, that makes sense. So we're adding more mass, the pressure is going to be higher inside the syringe. Higher pressure gas occupies lower volume. So lower volume occupied at high pressure. As for second mark, oh yeah, so if we have a high pressure, right, this drink is going to release its gas at a lower rate. So at high pressure, our whatever carbonated drink releases gas slower. Okay. Calculate the percentage decrease in final volume of CO2 per 100 gram mass placed on the piston using results of experiment 1 and experiment 3 at 100 seconds. 100 seconds. Okay, experiment 1, we have, I would draw the line, but just lazy, so 33. And experiment 3 looks like it's in the middle of that, which is 11.5. Okay, and then once percentage decrease, so 33 minus 11.5 over the initial again, which is 33. Percentage decrease, yeah. So per 100 gram mass on the piston. Oh, it's per 100 gram. We have 4. Okay, so if it's per 100 gram, we'll times it by 100 over 4, because we have our 400 gram mass here, and it wants to give it us per 100 grams. So we're essentially just dividing by 4 afterwards, but we'll include it in one calculation just for that. And it'll give us 16.3%, and that's per our 100 gram mass. Sketch and give a reason for a graph of the total mass of the apparatus in experiment 1 over time. Total mass of the apparatus in experiment 1 over time. We're not adding any weights. The mass of apparatus, so the whole apparatus. Syringe is there. Okay. So I think the graph will look like this. And reason is we have a closed system, right? So we'll have a constant mass regardless of the changes, right? In volume of gas and amount of liquid, our total mass will be the same because it's a closed system. The mass is not going to change. Oh, there we go. So yeah, that was the paper. Hope you guys enjoyed, and I'll see you guys in the next one. Yeah, pretty decent paper, pretty quick, not too many challenging questions. Yeah, so you guys should have had a pretty easy time with that one, and I'll make a new video pretty soon. So hope you guys enjoyed. See you guys in the next one.